Hello, AP Chem students. Sorry that I'm not here again today. So we're going to do a short video lecture. I promise it's going to be short. Over half-lives. Okay, so some of you guys might have actually already been exposed to half-lives and stuff in math class because I actually walked by like a math 2 class the other day and they were doing half-life. So I was like, whoa, this is awesome. Okay, so but anyway, in chemistry, what is a half-life? Well, half-life is just referring to the time required for the concentration of a reactant to reach half its initial concentration, right? So in other words, so concentration of A at time half-life, all right, time 1/2 is equal to half concentration of A at time 0. Okay, so it's just a short way to describe reaction rates. Reaction rates. Okay, if it's a fast reaction, equals short half-life times, right? All right, so it's still, in terms of our order of our reactions, we still, a lot of times these are related to integral rate law problems and stuff like that. So we definitely want to know whether it's zero order, first order, second order, and a lot of times they're going to let you know that in the problem. Okay, so, and we actually, are kind of expanding on this a little bit, and we're just going to jump right to giving you the equations, okay, for each half-life and for the order of its reaction. If you want to see the derivation of it and where this equation is coming from, you can head to the class website on the Google community and stuff, and you can search through there, and you can find it online there. If you want to see, a sub in 1/2 A sub 0 for the concentration of A and solve it for there, you can go and check that out. All right. Oh, but I'm going to avoid doing that. And if you want to just take my word for the derivation, here it is. Okay. So let's take a look at some graphs and stuff. Well, actually, I guess before we do that, quick little math note. If you have a fraction in our natural log situation here, which does pop up from time to time, just keep in mind that the natural log of 5/7 does not equal natural log 5 divided by the natural log of 7. It actually equals this. You've got to do the natural log of 5 minus the natural log of 7. Okay? So just be careful with that when we move forward here. Okay? Our reaction, you'll notice here, this is a reaction progress. I'm just putting this up here in general. Start at the beginning, which is 100%. All right, and as the reaction goes towards its end, all right, and each one of, we're looking at the percent reactant here, okay? So this is the first half-life. This would be the second half-life, and the third half-life, and the fourth half-life, okay, as things are progressing through the reaction. All right, so that's how much reactant is left over. All right, so that's kind of how we're going to talk about this in terms of reaction progress and like number of half-lives and stuff. So all about, we have our initial concentration, and we half it, and then we half it again, and then we half the remaining amount. And so ultimately we go from 100% of it around only 50%. And there's only 25% left. And then half of that is 12.5%. And then half of that is 6.25, and so on and so forth. Okay? Oh, this is how a graph would look for each of our reaction orders. For this one here, we got a zero order reaction, and we have concentration versus our time. Okay? Notice with a zero order reaction, the time of each successive half-life decreases. Okay, it decreases, and this is also depends on concentration. Okay, That's something to be aware of. Those are two things to be aware of. The most common type of half-life problem you're going to see is the first-order half-life problem, because they like to do these because they are not concentration dependent. Okay, they're not concentration dependent because you can see the concentration of the reactant decreases by 1/2 in the same amount of time. For each half-life.
Sub-plans, recap.
Hi, Mr. Weber, I'm recording. Yes, all right. So for the first order reaction rate, the concentration of the reaction decreases by 1/2 in the same amount of time for each successive half-life as it goes. Okay. Now for the second order reaction rate, or for the second order reaction, this one is dependent on, like the first order, it is dependent on concentration, as zero order was, but it also, you'll notice that the lower the concentration, the longer the half-life. Okay, so those are the graphs. So let's move on to a couple sample half-life problems. Okay, so if we look at these half-life problems here, the nice part is here, this one here tells you, hey, it's a first-order reaction, so it's telling you right away that it's first order. Okay, so that means that, I'll save you I'm going to flip to the front of the page. That means that T1/2, the half-life equation, is 0.693 over K. All right, and it's a first-order reaction that has a half-life of 20 minutes. Okay, so they want to calculate the rate constant for the reaction. So all we have to do is just plug and chug. We're going to use our equation, T1/2 equals 0.693 over K, our reaction constant, 20 minutes is equal to 0.693 over K. All right, we plug that in, and K will equal 0.693 divided by 20 minutes. So that's going to equal 0.0347 minutes. All right, so that's going to be our constant K. All right, so now the next part here is how much time is required for the reaction to be 75% complete. All right, so if it's 75% complete, that means there's 25% left over. Okay, if we go back up to our arrows, you might recall, hey, we had 100%, then it went down to 50%, then it went down to 25%. So that's first half-life, second half-life. Okay, so if we want to see that, hey, there's half-lives there. 2 times 20 minutes equals 4 minutes. Okay, so we can see how many half-lives in there, and if we know the amount of time it takes for the half-life, we just multiply it by that number. Okay, so you can do it like that, or we can do this another way, and we can use our rate law equation. AT plus ln A times 0. Okay, so we do this as well. All right. And what we do is, I'm just going to move this over here because it doesn't have enough space. Natural log concentration of A minus natural log concentration of A at sometimes 0 is equal to minus KT. All right. And I know, so natural log concentration of A, or the natural log concentration of A at sometimes 0 is equal to minus KT. All right. So now I've got this in there where I can do this. So if the natural log, and we got 25% left over, so I'm just going to do this as 0.25 in terms of the concentration. And at the concentration at time 0, I'm just going to say, hey, that's 1. Okay, so 75% of the way done, we got 25% left over. Okay, and we know that our K is equal to negative 0.347 per minute at T. Okay, so we just do a little math here. The negative 1.386 over a negative 0.0347 is equal to t. So t is equal to 40 minutes. So you can do it that way, okay, and you can use the equation that's given to you. And sometimes you'll have to do that, but hopefully we're going to try and do it a slightly different way and use some factorials and things like that, especially if we can see the number of half-lives that are present within the equation. Okay, so I just wanted to show you that for completeness. So if you wanted to do that, or if you're totally stuck and you can't quite figure it out, or you don't feel right about it, you can always resort back to those equations that you have on our cheat sheet there. Okay. All right, so let's do another one here. So the rate constant for and by the way, pause the video if you got to, if I'm moving too fast. All right. So the rate constant for the first order transformation of cyclopropane is 5.4 times 10 to the minus 2 per hour. What's the half-life for the reaction? What fraction is the cyclopropane remaining after 51.2 hours? And what is the fraction of 8? What fraction remains after 18 hours? Okay, so let's do part A here first. So that's going to be this first question here. Say that's part A. So they want to know what the half-life is for the reaction. So T1/2 equal to, because they're telling it's first order, 0.693. It's the most common half-life problem. 0.693 divided by 5.40 times 10 to the minus 2 hours. So that's equal to 12.8 hours. Or half-life is 12.8 hours. All right, so the next question I'm going to call part B. Next part of this question, what fraction of the cyclopropane remains after 51.2 hours? So the way I would do this is we have 51.2 hours have transpired, and we know that 12.8 hours is our half-life. So this tells us that, hey, 4 half-lives have gone by. All right, so what that means is we have 0.5 times 0.5 times 0.5 times 0.5. Because half of it is going by every half-life. So 0.5 times 0.5 times 0.5 equals 0.0625, right? Okay, so if you wanted to, you could always factorial that, or just take 0.5 and raise it to the 4th power. You get the same thing, right? All right. Well, for part C, what fraction remains? I'm going to call that the last question here. What fraction remains after 18 hours? So with this one, sure. Hey, you know what? You want to do natural log of A is equal to minus KT plus natural log of A at sometimes 0. You could do that. Go right ahead. Dial it in. All right? You can do that. But I'm going to do it. I'm going to take 18 hours. I'm going to divide it by that 12.8 hours. And that's going to give me 1.406. All right? That's telling me is, hey, 1.406 half-life has gone by. So what I'm going to do is take 0.5, raise it to the 1.406, and that will tell me what fraction is left. I've got 0.377. Okay? That's how much is left over. That's the easiest way to do it. Okay? I like the more portion here and just dividing the half-life, or dividing the amount of time divided by the half-life, and then taking 0.5 to that power. All right? It's a nice, simple, easy way to get there. All right. So there you go. If you feel pretty good, that's great. All right. Last problem, but if you, OneNote. Oh boy. OneNote's restarting, and it's crashed. Okay, so I guess maybe I'm not doing the last problem for you today. That'll be that, I guess. Okay, that stinks. All right, well, maybe I can pick it up in some period. Here we go. Am I still recording? Yes, I am. All right, this is great. Okay, so I'm going to go down, and we'll do the very last problem here for you. It's very similar to what we've done to this point at this time. So, but I'll work it out for you real quick, and you're well on your way. If you feel pretty good, you can get rolling. Okay, so an aqueous solution of hydrogen peroxide here that is 6% hydrogen peroxide by mass is density 1.03. Calculate each of the following. So, I want to know the number of moles of hydrogen peroxide in a 125 milliliter sample if it's 6%. So, 125 milliliter sample, we've got 1.03 grams per 1 milliliter because you got to figure out how many grams are in there. So we got 128.75 grams of H2O2. I'm going to multiply that by 0.06 because it's 6% solution. So I've got 7.725 grams of hydrogen peroxide in there. And they want to know the number of moles. So we've got 1 mole of H2O2, and it is 34.02 on the grams. So we've got a total of 0.227 moles of hydrogen peroxide in there. Okay, the number of moles of oxygen that are produced when all the hydrogen peroxide in the 120 milliliter sample decomposes. Okay, so we've got 0.227 moles of H2O2, and all we're doing mole ratio here, 1 mole of O2 for every 2 moles of H2O2, so we get 0.1135 moles of O2. All right, great. All right, on to the half-life problem. So we've got decomposition of hydrogen peroxide here. So we've got 2 graphs. Hey, this graph is curved, that graph is straight, right? Hey, guess what? This is what we want, right? And look at, we've got the ln of H2O versus time. Ln of H2O versus time, guess what? That's first order. All right, that's first order. Okay, so that's gonna, so here, right down here, they ask for the rate law. All right, hey, we've got rate is equal to K times concentration of H2O2. How can we justify our answer? Hey, well, that graph right there of ln of concentration of hydrogen peroxide versus time is first order. That's all you got to say. All right. They want us to determine the half-life of the reaction. Okay. So in order to do that, I just need to take a look at the graph. Okay. Let's take a look at the graph. So when it goes from, it looks like, so we start at 0 and we want a time of about, or we want, let's see, looks to be right about 650 or so, T1 half. So what is this right here? So it goes down about, wait, hang on, 0. I've got to come over here for half-life because I'm looking at, you got to look at the concentration. I don't know why, because that's why I was making. Okay? I got to come over here to the other graph to use the half-life here because, all right, it starts at 1 and it goes down to 0.5, right? Up, right there, down to here. So what do you think that is? That's got to be like about 650 minutes or something? I'm saying it's like 650 minutes, somewhere in there, 600, 700 minutes. It's definitely not 700, because that's 400 there. I'd say it's 650 so, all right, for half-life, okay? And they want us to calculate the value of the rate constant K. So all we got to do, because it's first order, right? We got a first order reaction, so T1 half is equal to 0.693 over K. So 650 minutes is equal to 0.693 over K. So K is equal to 0.693 divided by 650. So I've got a K equal to 0.0010, and that is in minutes. Okay. Hang on 1 second. Okay, so for the last part here, all you got to do is you're actually going to use the natural log of concentration of A is equal to minus K T plus natural log concentration at time 0. And it's just, we just got to plug it in for 2,000 minutes. I mean, you can estimate from the graph, like here's 2000, right? So you can estimate, well, maybe it's like 0.15 or something like that, or a little bit above that, right? So you got an idea, but they're going to want to see you calculate it and use this equation, and you know it's first order from the other graph. We just gotta, we're solving for the natural log of A is equal to minus 0.0010 times 2000 plus natural log of 1. Nice part is natural log of 1 is just 0. So natural log concentration of A is equal to 0.001 2000. So we got -2. So we just go E to the -2 is equal to concentration of A. So concentration of A is equal to 0.135. There we go. All right, and that's it. All right, folks. Hope you have a great day. I'll see you later. Let me know if you have any questions. Get rolling on that UT homework and see if you can't do that pre-lab question. It is an integrated rate law sort of deal for the pre-lab stuff. All right, talk to you later. Peace out.